All right, so we'll go over the basics of walking through how to use Matlab in general and then how to apply it to problems, just kind of an overview of everything. So first thing, what is the breakdown of what's in Matlab? So first we've got the variables. This is the numeric values, logicals, strings, characters, and symbolics, and a few others, but those are the main focus of this class. What we care about when solving engineering problems, at least in standard situations. So from those variables, you construct structures. These are the matrices, cells, structures, the things that are built off of the variables. And from those structures, you can do computations. So this is numerical operations, logical operations, character and string operations, and symbolic operations. So then we've got functions next. There's that which we've got built in as well as our own. So there's the built-in. This is like trigonometric functions, absolute values, square root, ones, all sorts of things. Those are the built-ins. There's also the anonymous. These are ones built into the same file. And then there are functions written with their own files. All right, then there are loops. These are repeated operations. Primarily, this is for and while loops. For when you're trying to go through a series of values and perform the same operations with each new value. And while you're trying to continue going while you still have some condition being met. And then finally, you have the I/O. This is also known as input-output. This is talking about what you actually generate out of a program, what you take into a program. So there's things like text I/O. This is the command line. And there's things like figures, plotting, and GUI for more complicated stuff. This is for graphical user interface. All right, so what are various aspects we want to understand in programming? So what are we doing with programming? We're trying to solve problems. So we have the tools we've got, problem we're trying to solve, and we go back and forth in order to solve that. So let's look at an analogy. Let's say you're building something physically. First, you have the materials you can work with. Then you've got the forming of the structures, right? This is, forming a beam from raw material. You're building brick from raw material. Next, you've got building and assembling structures. This is once you've got the structures, you're building them into some residential house, you're building it into a hospital, whatever you're building something from those formed structures. So in this analogy, material would be the variables, structures would be the normal structures like matrices. Building and assembling the structures would be the computations. This is when you're performing operations on the structures. Next, you've got the functions. These are in building a plan or a diagram. This is floor plans. This is how you know what operations to do. So it's pre-structured descriptions of the computations and things to perform. And then you have multiple operators working or repeated operations. So this is the loops. So this is when you have multiple people working on something. This is when you have yourself doing repeated operations of the same thing. Like you put an L in right here, and then you perform the same operation, but you do it here, put an L in, put another L in, put another L in. You could describe the breakdown of what you're performing that way. That's what we'll do in programming. And then you've got the structure, the actual output, right? Down here we have finally the input output. This is in building, just going to be things like, what are you actually outputting? Is it the structure? Is it like the variables? that you're outputting? Are you taking a picture and sending it to them? Are you giving a text description of what was done, how to do things, whatever? All right. And so this is a sort of analogy to a physical operation of how you would perform the same thing in a programmatic manner. All right, so now these are kind of the building blocks. What are the actual steps we perform to go ahead and make a program? So first, you've got steps to make a program. So one, how would you do this manually? So this is going through the process. Okay, we've got some work to do. How would I actually approach this myself? So that you know what steps you can take programmatically to do the exact same thing. So next, you want to figure out, okay, what programming elements are involved? So in order to do the thing that I did manually in a program, what are the sorts of things I'll need to include? So this is things like, what are the variables and structures, right, that I'm going to have to incorporate here? Then next, you want to look at, okay, what are the computations I'm going to be performing? So we've got our elements. Now we're doing the computations on those elements. And you want to see next what functions you want to use. So there's going to be some built-in functions. Do you need to make a new function to make this easier, make it faster, simpler, whatever? And then finally, or second to last, we've got what looping, including nested loops, we're going to need. So are we performing repeated operations? And am I going back and doing the same thing with a different starting point or whatever? So am I going to need to loop this to perform repeated operations? And then include nesting, so a loop within a loop, which we'll talk about later. And then what outputs have we got here? So this is things like the input and output, figures, graphical user interface, which is just a window like in a browser where you have information displayed or whatever. So how are we going to show what's actually going to be produced from this program? All right, so let's look at the analogy. What does this mean in the analogy? So what programming elements are involved? This is the variables and structures, right? So in our analogy, that is what materials and structures are we going to need to solve this problem? And then we got which computations to perform. So what building and assembling structure of these structures are we going to have to do? So what operations are we doing on these materials and structures to get them in the shape we want? All right, and then what functions to use? So these are, do we have any good floor plans we can work from? Do we need to use any pre-made instructions to solve this? How are we going to use what's already been done to make this faster and easier? And then the looping is what repeated operations. Are you going to do the exact same thing? Are you going to build something right here and then build something right here, but use a little bit different instruction there, but it's basically using the same floor plan, so you can just loop it and do the same thing over. And then what outputs and construction, this would be things like what's the actual structure you're outputting, what are the pictures, description, plans that you're getting out of this. In a program, this is going to be some text, some variables and structures, certain figures, graphical user interface, whatever. Okay, so building off what we were talking about before, what are the building blocks of our programming skill set? First thing is the variables. So how do you make a variable? In Matlab, you just say var name or whatever the name you choose for your variable is, and then equals whatever value. There are the different types of values. You can have numerical values, you can have logicals, strings, characters, symbolics. Sparse and categorical are more if you want to either, in the case of sparse, simplify the information, or categorical to store categories of data so that you can break it down and see what sorts of elements are within that and the frequency of them and such. And then another data type we have is date and time. and this is just store date and time data like you might expect. So there are also built-in variables. These are things that are already in Matlab that have been pre-constructed. This is things like pi, that's of course 3.14, dot, dot, dot. All right, now we got structures. So in Matlab, this is things built off of the base variables. So the base data types. With structures, we got matrices because Matlab is the matrix laboratory. Basically, everything's structured into matrices. So here we can construct a matrix by using the brackets to input. And with this, we can say define a variable equals to some matrix of values. So we use the commas to separate a new column and the semicolon to put it into the next row. We can also specify, okay, be at all the rows, all the columns, first position in the third dimension is 2, 2, 3. In the first row, 4, 5, 6 in the second row. And then we could specify be at first row, first column, first in the third dimension would be 1. And that would make B back into this A, because the only difference between these two is if we change this to a 1, we now did that, so that's how that would work. So let's say, what does A look like? Let's do a quick review. A is going to be 1, 2, 3, 4, 5, 6, right? Let's put this over here for clarity. And the way we can define any point in this, let's say we want to look at this. We want to do A of, and then use parentheses. Brackets are how you define a matrix, right? But to call up a certain point or refer to positions in a matrix, you use the parentheses. So A of row would be first, so that would be the first row, second column, and then first in the third dimension, but it will automatically assume first in the third dimension. So in order to call this, we could do this. We could also specify the first in the third dimension, and that would give us 2. So if we just said like B equals that would make B equal to 2. And if we did this equals 3, that would override that value with 3. We can also look at multiple locations. We call it invert color. So let's say we want to look at these 2, and then let's look at these 3. So this would be the 1, 2, and 3 would be A of all, or excuse me, the first row, all of the columns, and first in the third dimension. So the colon is referring to everything in that. So this would equal 1, 2, 3. And if we did this, it would do nothing because it would just override 1, 2, 3 into this, which is already 1, 2, 3. Okay, so now for the 4, 5, we can say A of row 2, and then this would be columns 1 and 2. So the way you do this is you say starting point, that's column 1, and then colon, meaning up to some point, 1, 2, column 2. If we wanted to include all of them, we could also do 1 to 3, but we only want 4 and 5 this time, so 1 to 2, and then we can either include the 1 or exclude it for simplicity's sake. This equals 7, 11. That would then override 4 and 5 with a 7 and an 11. Right? There we go. Hopefully that makes sense. That's the main thing we deal with in Matlab because it's the matrix laboratory. So next we've got cells. Cells can fit multiple types of data together. So you can fit matrices, you can fit strings. In this case, you can fit characters, numerics, all in one cell. So with a matrix, you can only have one data type. So I could have hello and you. And that would be a matrix. You couldn't do hello and 1. That is not possible for a matrix. So there we would have to do hello with a cell, which is the curly braces, hello, and 1. That would allow us to fit multiple types of data in there. Next way to fit multiple types of data, we've got cells, we've got structures. So structures of data, we use the period to call up some element in it. So let's say we've got the structure planet, and we want it to have a couple keys in there. Cont, short for continents, elm, short for elements, animals, and species. So to specify the continents in the structure planet, we could use a matrix with North America, South America, Europe, Asia, and Africa. And there's more here, but just for simplicity's sake, I just included those. The next, you can include elements. So here we've got things like hydrogen, helium, lithium. You can go on, fill out the whole periodic table. And we've got the animals in this. So planet.animals. This is horse, eagle, turtle, cheetah, etc. All sorts of animals. Then species. This is another structure. So planet 2 would be its own structure. Planet 2.species, and this would be a new set of species on whatever this other planet we're talking about is. And we can refer, I just happen to want all matrices of strings in here. You could put other data. You can put a cell inside .cont. You can do whatever. And you can refer to these just like variables. So you can do planet2.species. And this is effectively the variable name now. So I could just pretend that the dot isn't there, and this is like planet2_species or whatever, some other variable name, and call up the first element, for example, in orc. Or the first element in .species, which is orc. So this would equal, or this would return orc. All right. So the next step, we've got the variables, we've got structures, now we've got computations, right? So a way in Matlab to find the computations is use the command help and. So to see this, we can go into Matlab, help, and if we scroll up, it shows us all the operators and special characters. So this is plus, minus, star for multiplication, this for division. You have relational operators, equal, not equal, less than, greater than, less than equal, greater than or equal to, and or not. Then we've got special characters, colon, parentheses, and subscripting. So when you call them a function or a place in a matrix or whatever. We've got the brackets to define matrix, curly braces to define a cell, at to define a anonymous function, grid for decimal point, or to subscript to a key in a field, or in a structure, and so on and so forth. So we go back right here. So we've got basic things like arithmetic. So we have addition, subtraction, multiplication, division. So with normal numeric values, we have c equals 1 plus 2. This will output 3. Obviously, we can also use variables a and b, just as we could use 1 and 2. We can substitute those for variables. This is 1 and this is 2. So these two are the exact same thing. So this would also return 3. 1 divided by 2, this will return 0.5. And 1 times 2 will return 2. So pretty obvious, just the basic stuff. There's also the caret, which is for exponent. So like 3 to 1. 3 to the power of 1 would be 3. 3 to the power of 0 would be 1, so on and so forth. And then, as we were talking about a little bit a moment ago, we have the conditions. So the main ones here are arithmetic and conditions. And the way we have our conditions is we're going to use comparisons to change numerics, because this is all about numerics. We're going to use conditions to change numerics to logicals. With this, so conditions to logical, we got equals, which is two equal signs, not equal, the similar sign, or can't remember, that may be called ampersand, and equal. So that's not equal. The reason, you got to remember, equal is used to update a value of some variable, so you got to use the double equal as a comparison operator. You got less than or equal, greater than or equal, greater than equal, less than, and greater than. So for example, you got 1 equals 1. This will return true. 1 does not equal 1, so of course be false. And just as with arithmetic, you can substitute values in. So a equals b. In this case, a is 1, b is 3. So a does not equal b. So a equals b will be false. But a not equal b will be true. All right, so now we got our computation, but of matrices. So this is slightly more complicated than just scalar variables or singular values. So when it's got a matrix that's got an array of multiple dimensions, either it's 1, 2, 3, for example, or it could be 1, 3, 7, 9, or it could be layers. So 1, 3, 7, 9, and right behind it, we've got 2, 4, 8, 11, and right behind it, 3, 6, 9, 10. And that would be split into the third dimension, so layered on top of each other. Just remove that for simplicity, so it's not confusing. All right, so here we've got a vector, because when it's a single element, that's a scalar. When it's along a length, it's a vector. And when it's so scalar, vector, and matrix. Okay, so this, we got our vector and another vector. Now these are the same size, so if we just want to add these two, we can just use the add operator. If these weren't the same size, then it wouldn't know, like, if we had an extra 1 in here, say we add 5 to the end here, what is this one going to do when we try to add it? It won't know. So to add matrices together, they have to be the same size. So we just add 1 and 2, 3, 1 and 4, 5, 5 and 2, 7, 4 and 3, 7. Okay, and then a minus b, that would be value in a minus the value in b, -1. You can go check all these. You got a dot divide. So this is, again, element by element. So when you use the dot for multiplication, division, and powers. We'll just do element by element. So it'll be all the elements in A divided by the corresponding elements in B, all the elements in A multiplied by the corresponding elements in B, all the elements in A to the power of the corresponding elements in B. So 1 to the power of 2 is 1, 1 to the power of 4 is 1, 2 to the power of 5, 32, 3 to the power of 4, 81. All right, you can also add, subtract, divide, multiply into the power with scalars for matrices. So I can add 1 to this matrix. It'll just add 1 to everything in that matrix, subtract 1 from everything in that matrix, divide 2 everything in that matrix, and so on. All right, on the other hand, we have matrix multiplication and division. This is linear algebra. So in linear algebra, you'll multiply two matrices together. So when you have a matrix like this, multiplied by this matrix, the way this will work is you'll multiply 3 with 1 plus 4 with 3, 4 times 3, then 3 multiplied by 2, 6, plus 4 times 4, 16. And then 5 times 1 plus 6 times 3, 5 plus 18. 5 times 2, 10, plus 6 times 4, 24. And then you fill these in. If I put this into Matlab real quick, go to Matlab, we do 3, 4, 5, 6, multiplied by 1, 2, 3, 4. Got 15, which is 12 plus 3. We found 4. 15. That's the 12 plus 3. Got the 22. That's the 6 plus 16, and so on. You can see that's how that works, and there are many reasons you do that, but it'd just be like if you have physics class that's doing matrix multiplication or division or whatever, that's how you perform it. Is in MATLAB, you use the single asterisk or divide to do multiplication and division. We also have transformations. You can do a prime or a apostrophe that will transpose the matrix, and then you have lots of built-in functions. Of course, you have INV that will take the inverse of a matrix, and so on and so forth. Okay, so now we've got logicals. So in computations on logicals, what can you do? Logicals have a bunch of different operations. So with them, we can do comparison operators. So just like we did with the numbers before, you can say true equals true. This will test if true is true. If false is true, that's obviously false. False is false, so this would be true. But you also have operators to compare a set of things. So for example, you can do true and true. This will mean both of them have to be true. So this is true. True and false is false. False and false is also false. This is or. So true or true, that'll be true. If anything in a series of ors is true, then it'll be true. So if you had like true or false or false or false, that would be true because there's at least one true in there. In addition, you can use the and or just as you can with logicals. You can, when you do 1 is less than 3, for a comparison in the numerical, this returns a logical. So 1 is less than 3, so that would be true. So if you want to know that 1 is less than 3 and 3 is greater than 11, or let's say you want to know or 3 is greater than 11, you can use an or operator there, because this will return this true or this false. So there, in that case, one of them is true, so it will return true. Another important thing is all of A, or any of A. So if you have a matrix where you've done an operation, so A is 1, 2, 3, 4, and you say A is less than 3, then this will return true, true, false, false, right? So if you did any of, let's just call this B equals A less than 3, any of B equals, or that will return true. All of B will return false. Okay. The next thing you can do is statements with logicals. So you can say if condition 1, then do operations 1. And then should condition 1 be false, you don't do operations 1 and you immediately go to else if. This is upon this being false, we have another condition we want to check. So we have condition 2. If this is true, then we'll do operations 2. If not, we won't do operations 2 and we'll continue to the next. We can have multiple else ifs after this, but you don't need to. You don't even need else if or else. You can just do if end. But you got if, else, else is upon everything above it being false, no matter what, perform this operation. And then end, you need end to close out the if statement. And again, you could condition 1, this could be 1 is less than 3. Just like this returns a logical. So if logical, so you can do any series of some set of all of some matrix is greater than 3 and all of some other matrix is less than 11. You do whatever in this condition, and whatever operations you choose in this operations. All right, for string computations, there's not that much that we really care about. The main thing is if you add strings together, you'll just put them together as one string. So if you add A with B, that will return A, B. Without a space or anything, it'll just be A and B together. So if you add the string hello with period, and then add that to space, and then add that to how are you, you'll then have hello, period, space, how are you. If I can fit this all in there. And that will be how that will work. All right, as for characters are similar to strings, right? They're just single character of, say, 1. You can make a character 1, you can make a character B, you can make a character semicolon, you can make a character period, anything like that, right? And you use the single tick to designate a character. So operations on characters are more complex. They're basically just how a programming language functions. So if you try and like add two characters together, it's not usually useful for solving engineering problems, but just as an overview so you have an idea of what's actually going on. A plus B will convert A and B to numerical values. It'll do a bitwise computation based upon that and add them together. So if you did if I open Matlab, here we are, and I do double of the character A. That'll give me 97. Double of the character B. That'll be 98. So 97 plus 98 is 195. If I do A plus B, I'll get 195. So that's what that's doing. It's converting it to a numerical value and then adding those numerical values together. All right, now for symbolics. So symbolics, they're variable types just like strings or numerics, right? So you can have sims and then all the symbolic variables you want to define. Sims var1, var2, var3, var4. Then you have sim var1. Another way to generate var1 is a symbolic variable. And then you can have some symbolic variable equal to some function of symbolic variables. So var1 plus 2 times var2. This will create the symbolic variable symbolic. You can also do equations. So we can make an equation is some function of symbolic variables where there's a condition here. So in this case, it's the double equal. So it's specifying, yes, it does equal, because single equal obviously defines a variable. So double equal, so that's saying var1 plus 2 times var2 equals 3 times var3. And then you can use operations on those built-in functions to solve that, to substitute in, perform different operations there. All right, next up is functions. So first we have the built-in functions. These are the things you can open immediately when you run Matlab. So when you open it right off the bat, you can say ABS of -1, it will return 1. There's basic mathematical functions like that. There's stats functions, matrices, ones to make a matrix of ones, size to get the size of a matrix across all the first, second, third, however many dimensions you've got, length to return the highest along any dimension, so the greatest of any of this values in size. You've also got sims, lots of functions to do with that, solve, subs, diffint, desolve, numerical techniques like interp1, polyval, polyfit, plotting, plot3, fplot, and more. In addition to this, you can create your own functions, which is just a way to create pre-constructed computations for anything. So there's two sorts of functions here. We have anonymous functions that are within your same file. So you can just put it up above wherever you want to call this function and use the function name to refer to it. So let's say you have a function, you want to name function name, use equals and at. At is telling you its function handle. Then the parentheses, however many inputs you got, you could have like variable 1, variable 2, you could call them A, B, whatever you want. However many inputs you've got separated by commas. And then you have output computation. This is like take the sign of the input and multiply by 2 or whatever the computation you're performing is. This is limited in that you can only fit into this function what fits in a single line of computation. You can't do like loops with an anonymous function. But here's an example. Let's say you want to make a function absolute value that takes the absolute value. You call it absolute value equals at, and then parenthesis in var, because you just have one variable. I just chose to name it in var. ABS of in var. And then if you do absolute value of -1, like that, if you do absolute val of -1, that will return the same thing as ABS of -1 or +1. The next is your own file function. So in this case, you can have multiple outputs, unlike the anonymous function. So you say function, bracket, outs, however many outputs you have separated by commas. So you could have 10 outputs, you could have one output. Equals, and then function name is the same as up above here, whatever your function, when you reference it, like absolute val up here, whatever you want to call it, and then inputs in parentheses after that. That can again have many inputs, all separated by commas. And then you have whatever operations you want to compute, the outs, and then end. So for example, pretty basic one, you have the function p equals pv nrt of the inputs v, n, r, and t, and then it'll compute p equals n times r times t divided by v and end. So now if you call up this function, we can then do pv underscore nrt, same as right here in the function, and then feed the inputs 10, 1 to the negative, times 10 to the negative 3, 2 times 10 to the negative 3, and 250. Whatever's just placeholder values for v, n, r, and t, and it will then compute 1 times 10 to the negative 3 times 2 times 10 to the negative 3 times 250 divided by 10. And that will give you the pressure. All right, now on to loops. So loops are composed of two possibilities. One is a for loop, the second is a while loop. In a for loop, you go through all elements in some array, and in while loop, you repeat until some condition is met. So here's the structure of a for loop. For n, this is the variable that will receive the new value for each element in the n's, and then it will perform operations. So more specifically, it loops with n equaling the first, then the second, then third, going on, element in n's until all the n's have been gone through. With the while, it loops without changing n. Instead, I should say the looping ends with the condition of n is less than n max is no longer met. So in this while loop, you will typically change n so that n will, once you've gone through everything you want to, it will no longer meet this condition, and then it's done. All right, so for nesting loops, you can nest loops, which means looping within loops. So for nesting loops, you have for n equals n's, and then some computations, then indented, as you can see, also with the computations, for m equals m's, because you would want the n and the m to be separate variables, otherwise it would override, it wouldn't work like you would expect. So for n equals n's, and then for m equals m's, then whatever computations in here, end that first for loop, do whatever computations here, and n, and the outer for loop. So first, this will assign the first value in n's to n, then it will perform computations 1, then it will assign the first value in m's to m, then perform computations 2, and then we'll go back, because it's a loop, it will do the computations 2 the first time, circle back, m will now equal the second value in m's, then it'll do computations 2, circle back, m is the third value in m's, computation 2, circle back until all the m's have been gone through. Then with the last value of m and the first value of n, you computations 3, and then you reach this n, so you circle back n equals n, so n is now the second value in n's, perform computations 1. M gets the first value in M's from computations 2, while N is the second value. Circle back, M is the second value in M's, blah, 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 until you get all through all the M's. Get through until you have circle back to every N's. Then for that final N, gone through every M's, and then exited. All right. So to see a little bit of an example of this, if you have a series of loops, you'll just have for n equals n's, computations, and then end. And then following this, for m equals m's, computations, and end. So in that case, you'll just go through all the n's in the first for loop, and then you go through all the m's in the second for loop. But like in this case, where you have it nested, you have a for loop within a for loop. You have not a series, you have a nested. So in that case, n equals 1, then go through all the m's. N equals 2, then go through all the m's. N equals 3, then go through all the m's. And these are just an example of what the n values could be. This could be any set of values. It could be 1,000, 223, 767. It could be strings. It could be any series of values that you then loop over with n. Or you could do a while loop and then have it be conditions to be met. Okay, now there is I/O. So I/O is input and output. I is the input, of course. O is the output. So for the most basic input and output, you can have text. So this is like in the command window when you say input, when you say disp, short for display, things like that. When you just call up a variable, that is displaying an output of text, or with the built-in function input, you can call an input of text. Then reading and writing to and from files. This is another example of input-output. So you can have like generic files, you can have images, you can have data files. Each of these you can read and write to in different ways in Matlab. Then there's generating plots. You can just use like plot, plot3, surf to generate plots here. Then you have generating animations and movies from plots. This is doing plotting and then using draw now or get frame to create an animation or a movie from the changing within that plot. All right, then there's the GUIs, or graphical user interfaces, or GUIs, all referring to the same thing. In a graphical user interface, you'll typically have something like buttons, a text entry, text display, plot displays. You may have like in interactive drawing canvas, you could like force it to draw lines or shapes or whatever onto it. Many different options there. With the standard I/O, these are a lot of the main functions you'd use. fopen to read or write to files, imread and write to read and write images, draw now and get frame for animation of plots. Then there's also the GUIs, typical functions you would use here is like UI figure, UI panel, UI button, UI axes, and you can find more in the Matlab documentation on the pages ways to build apps and develop apps programmatically. All right, so let's go into a little bit how you can use matrices. So first, how do you construct matrices? So let's just give a matrix that we want to create a variable name. We'll call it A. A equals 1 to 10. So a equals 1 to 10. In this case, we have 1:10. The colon operator lets us automatically construct a matrix, and this would just make A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, all the way to 10. And the reason for this is with the colon operator, you can frame it one of two ways. You can have the first number, the increment, and the second number, or you can skip the increment and it will automatically do increments of 1. So in this case, I skip the increment, it automatically goes from 1 to 10 in increments of 1. In this case, let's say we put in 3 colon 0.5 colon 5. That would make 3.5 for 4.5 and 5. All right, next, linspace. This is a commonly used one. This allows you to linearly space numbers from the first number, 1, the second number, 100, with 10 total numbers in between. So it'll automatically pick, okay, what's the increment we need to go from 1 to 100 in 10 total numbers, and then it'll have the same increment between each one. So if I pull up Matlab, and I go and I say linspace of 110. Run this, we'll automatically output this, because it will go from 1 to 100 with a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers, and it will say, okay, we need the increment to be 11 for that to span 1 to 110 steps. So, or with 9 steps really, because there's 10 numbers. So 1 plus 11 is 12, 12 plus 11, 23, all the way until you span from 1 to 100 in 10 steps. All right, so next, that's linspace. Next is ones. Is another commonly used way to generate matrices. So ones of 2, 3, 2 will automatically create a matrix with 2 rows, 3 columns, 2 in the third dimension, and no extra depth in any of the following dimensions. So this would be 2 rows, 3 columns, and depth of 2 in the third dimension. So it will be that, and then it'll also have another one behind it, where that's just layered up like this in a visual way. That's how that data would be stored. Okay, now in revising matrices, you just call up the matrix and then the row, column, and depth in the third dimension, or whatever specific elements you may not need this if you don't have a depth in the third dimension. And then you give it the matrix that should fit within that space. So in this case, it's all of the rows and columns. So it's just, in the case of A is this size, right? So we want it to be 1, 2, 3, 4, 5, 6 back behind. So we call up all the rows, all the columns, and the depth of 2. So behind right here would be 1, 2, 3, 4, 5, 6 instead of 1, 1, 1, 1, 1, 1. And in specific, Why is it colon here, 2 here? If it's a single number that you want to look at, like if we want to look at just this, we'd have A of the row, which would be 1, the column, which would be 1, and the depth in the third dimension, which would be 1. But if we want to look at multiple spots, so let's say we want to look at this instead. This would be, and let's say we want to look at this and this together. This would be A at, the row would be 2, the columns would be 1 and 2, so we'd have 1 colon 2 in this case, and then it would be both of the depths, which in this case is all of them, so I could just use a colon, expand that, or I could do 1 colon 2, do the same thing, and that would give me these 2 spots. All right, so that's how you do that. Like when you have a vector 2 where A is 2 colon 20, so it'll just be 2, 3, 4, 5, 6, 7, 8, all the way to 20, right? A of 1 would be 2, 3, 4, 5, all the way to 18, 19, 20. And then A of 1 would be 2, the first position in A, and A of 3 would be 4, the third position in A, because it only has a length. It doesn't have a 2 dimensions, so you don't need to refer to the row and the column. You just need to refer to how far along in this matrix you want to look at. And then when the matrix is 2D plus, you refer to however many dimensions you're caring about. So in this case, it's a 3x3 matrix. It doesn't have any depth like the one up here. So we just look A at row 1, column 2. And if A at row 1, column 2, which row 1 was the 1, 2, 3, row 2 is the 4, 5, 6, so row 2 is 4, 5, 6, column 2 would be 5, so this would be 5. And then row 3, column 2, what is this one? This would be row 3, and column 2 would be 8. So let's put 8 there. So in summary, referring to matrices, you have matrix of the row, the column, and however many. Following that, you can have third dimension, fourth dimension, fifth dimension, so on. R is the rows, C is the columns, and then you could have 1 colon 3 that spans from including all the rows 1, 2, and 3. Colon is all the columns, so if it's got 5 columns in the matrix, is all 5 columns. It would be equivalent to 1 colon 5. In 2, if you just care about one position in the row, column, or depth in the third dimension, you would just include one value. So in this case, I'm just looking at the depth of 2, like in this example, that would be the depth of 2, and this would be the depth of 1. Okay, as far as generating matrices, one I didn't talk about that you can also use, rand is a great function. It generates random numbers from 0 to 1, and then you just specify the matrix size. So I want 1 row, 10 columns. You can do more. You can do depth of 3 in the third dimension, depth of 4 in the fourth dimension, blah, blah, blah. And then I want it to go, instead of from 0 to 1, from 0 to 100. So I just multiply it by 100, and then now it'll develop a matrix like 50.6, blah, 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 with 10 randomly generated numbers from 0 to 100. In this case, a equals 1 comma 2 semicolon 3 comma 4. The comma is to separate the columns, and the semicolon is to move it to a new row. So it's kind of as if you were to just delete the enter, move it back up, and then use commas or spaces. You actually don't need to put a comma there. You can just put a space. Or a semicolon right here to separate when you're entering for a new row. So that's how you generate it with numbers that you actually know you want, like this. Then B is 1 colon 0.1 colon 10. So we'll start 1, then it'll go up by 0.1. Is that less than the 10? Yes. So 1.1, 1.2, 1.3, right? 1.4, 1.5, all the way up to 9.8, 9.9, 10, like that. Then you have linspace. Linspace will go from the first number 0, the second number 10, with a total number of 50 in between. So it'll automatically figure out, okay, I want 50 with a constant increment. So it just saves me the time of calculating what my increment is going to be, because this is the same as 0 colon something colon 10, but I don't have to calculate out how many, what that increment should be to have a total of 50. So with linspace, it'll basically do the same thing as this, but simplify it for me. And then A equals 10 times 1s of 2, 3, 4. This will be a tens matrix. So they all have value 10 with 2 rows, 3 columns, and depth of 4. So 2 rows, 1, 2, 3 columns with values of 10 in each of these spots. And then it will have 4 of them. So depth 1, depth 2, depth 3, depth 4. 1, 2, 3, 4. All right. Yeah, so that covers generating and manipulating matrices basics. Now, let's talk a little bit about when you'd use what in programming. So when would you use something specific? And how are you going to do things in a program? So they're the elements we talked about. Let's go over them a little bit again. There's the variables, right? This is anything you want to keep track of or examine or create will be a variable. Structures are fit within variables, but they're more complicated than the basic data structures of like a number, a string, things like that. With structures, you can have more complicated things like matrices, which are the foundation of Matlab, the matrix laboratory. So you can use matrices to call up specific elements in a single variable, iterate through data with for loops, things like that. You have cells, which store multiple types of data and allow a reference to specific elements in a loop, much like matrices. There's also structures, and that allows you to store data in blocks, and you basically branch out from the structure so that you have like okay. So for example, let's talk about a structure plants. Plants could have three elements branching out from it. It could have types, faves, cont, short for contained at specific locations. So in the contained, you could have home and work, for example. And then with each new level, you go follow it with a period, and then whatever. So to get to work, we would do plants.cont.work. and that would give us the part of that structure that we're looking for. There's also the computations. This is where you perform whatever operations. So in Matlab, it's a computer. It's made to do calculations, but this is like the things we standardly think of, like calculator, right? You can do that with Matlab. Then there's your functions. Functions are basically pre-constructed or pre-constructed in Matlab, or your own pre-constructed operations. So it's like a series of operations that you want to repeat, that you want to have built in some things so that you can use later as a like diagram of what computations to do. Then you would make a function. Looping is to perform repeated operations. You can iterate through structures. You can iterate through matrices with a for. You can iterate through values in a composed matrix. You can also repeat operations until a condition is not met anymore. And then there's, of course, the input and output text, files, plots, GUIs that you can actually get out of a program. So let's look at solving a problem in Matlab. So let's say we have this mass. It's 100 kilograms. It's got this force acting on it. Unknown force at some angle theta from the horizontal, and it's pushing this mass. So you have a 100 kilogram mass with the force F acting on it as shown. Coefficient of kinetic friction between the mass, this 100 kilograms, and the floor is 0.3, and the angle theta is 15 degrees. I want you to find the force necessary to accelerate the mass at 10 meters per second squared. So first step is to understand how to approach this problem. So let's solve it by hand. We have the exact same problem as before. Let's make a free body diagram like you do in your physics class. You have the force F, you have the weight, you have the force due to kinetic friction, and you have the N, or the normal force, acting up from on the block. So here we can break it down. Okay, some of the forces in X. This is F, the force here, times cosine of theta, minus Fk, the kinetic friction, is mass times the acceleration in X. Then you have the forces in Y. This F is acting downwards, so negative F sine of theta, negative W, and positive N. And this is mass times acceleration in Y, which it's not like bouncing up and down the block, it's just sliding along the surface. So there's zero acceleration in Y, so this would be 0. So we have the knowns theta, AX, M, W, which we know equals to mass times gravitational acceleration. And then force due to kinetic friction is the kinetic coefficient of friction and N. And our unknowns are F and the N, which is part of Fk. So we can solve these equations, and we can say F, force we're looking for, equals to mass times acceleration in X plus mu k N over cosine of theta. And going on with this, we can solve for N once we plug that F into some forces in Y equation. We get an N, and we can plug this in and say what F equals to. We can calculate M out or N out because we know all of these. We can just plug them in, and then we can plug that N into F and solve the problem. So that's how we'd solve it by hand, right? Solve a standard physics problem. Now let's solve it programmatically. So let's think about this. What sort of like mediums can we work with? What sort of materials have we got in our programming language, looking at it from a physical perspective? So our materials, we have numbers and symbolics, right? So these are the sorts of inputs and outputs we could want. Output, we want some number, right? But as an input, we may want to deal with symbolics or something to simplify the calculations we're actually performing. So let's look at using the numerical material. So in our physical analogy, right, we can go back to this. With our analogy, we have we're building something physically. We have our material. It's like our variables. We are forming the structures from those materials. It's the same thing as structures. We are building and assembling the structures. That's the computations. We have our plans and diagrams. That's the functions. And then we have multiple operators working, and we have repeated operations. Those are our loops. And then we have the actual output here, right? Give the structure actually what we built to them, take a picture, describe it, whatever it is. So these are the steps we're going to work through to solve our problem. So let's see, we're right here. We're going to approach this numerically. So we have our structures. This is the M is a known 100 kilograms, mu K, coefficient kinetic friction is a known 0.3, X is a known 10 meters per second, squared, theta is a known 15 degrees, and we want to find N and F. Our operations, well, we already solved for N and F ourselves, right? So we can just plug in, have Matlab do the calculation, N equals M times G plus MAX over cosine of theta. And we would have to use our order of operations, right? So we'd have to do this divided by this, with order of operations again being that, right? Mu K times sine of theta divided by cosine of theta. So that's how we were going to do it numerically, right? We already solved how to do the physics written out. So then we can write out, have Matlab do the computation. N is whatever it solves out as, F is whatever it solves out as. Then we have loops. In this case, it's pretty simple. We don't have repeated operations we're trying to do. If we wanted to go through and do some operation over again, or do something again and again for whatever, we would use a loop. Then we have our IO. In this case, very simple. We wanted to solve for F, so we would show the F. And again, this is the numerical. So with numerical, let's sum it up. We would solve it out as we did by hand before. And then we have Matlab do the calculations. So just so basically have Matlab be a calculator for us with handling the order of operations and everything in doing the computation. Next option was symbolically, right? So again, what materials have we got? The numerical and symbolic. These are the inputs and outputs we want. So let's look at the symbolic option. So in this case, our structures are just symbolic. So we have M, mu K, AX, and I'd have to, of course, name it something that Matlab can do. So like this would be A underscore X. This would be U underscore K or whatever. Then I have F times cosine of theta minus mu K times N equals MAX. And this would be a symbolic. I would create the symbolics here, sims, M, theta, N, F, all the variables here. And then I would say equation 1 equals F times cosine of theta minus mu K times N equals MAX. And that would give Matlab the equation right here. And then make the second equation equal to 0. equals 0. Then I would use the operation substitute the knowns into the equations and then solve the series of equations. So I would use subs, S-U-B-S, to substitute the knowns into these equations, and then I would solve the series of equations, and then again I would have no loops, I wouldn't have repeated operations. In the IO I would have f, or I would output the f to some answer variable I'm caring about, or whatever else. So then symbolic, let's go over again, how is this procedure going to work? We're going to 1, generate the equations by hand, and then 2, have Matlab solve the series of equations. Okay, so let's look at another problem to solve. So let's say we have a few points of data. We have these temperatures, 101, 102, 101, 104, 100, 101, 103, 106. And in the first row, we have day 1 data. In the second row, we have day 2 data. And then we have another matrix, time hours, time underscore hours, HRS. And then this would be the time in hours corresponding to these points of data. So let's say I'm like running some piece of equipment, and instead of keeping track with like hours and minutes that day, I'm just have a runtime. This is how many hours it's been running. So for this equipment, it's a temperature 101 when the equipment has been running for 1032.3 hours. Temperature's 102 when it's at 1039.6 hours, and so on. So I want to find the times where the temperatures are greater than 102. So let's see, if I'm trying to solve this problem in Matlab, what can I do? So first, I have the same problem here, but what am I going to do? I'm going to think about how I'm actually going to solve it with hand, or by hand. How would I actually approach this? So first, I would look at the first value in temps. In this case, it's 101, right? And then I would say, okay, if that temperature is greater than 102, add that to a list of the times that I care about that are greater than 102. So it is not greater than 102, so I don't add it to a list. So then I circle back. Okay, look at the second in temps. Okay, in this case, it's 102. Is that greater than 102? No. If it were, I would add it to the list, right? But it's not, so continue to circle back. Look at the next in temps till I've looked at them all. So now we're at 101 again. That would be the same as the first, so don't do anything. Next, 104. Okay, so now we've reached one that's greater than 102. I want to add that to a list, so I'm going to make my own little list here. Make my own little list, and I will include the time corresponding with that, which in this case, it's 1, 2, 3, 4 over on the first day. So row 1, column 4, 105.1.1. 105.1.1. And then I'll go through and add all the other ones. Just repeating the same process. Look at the next value, 100. Is that greater than 102? No, blah, blah, blah. Going forward. So I'll have 105, 1.1, 107, 1.3, and 107.5 at the end here. All in a list. Okay, so now how am I actually going to do that programmatically? Well, the main way I'm going to do it is using a numerical approach. So like before, we could do lots of different basically material types, right? We have symbolic, we have structures like matrices, and so on. So in this case, we want to deal with numerical things. So let's start. With programs, I typically open with clear CLC close all, where clear is going to erase all the variables currently stored in the workspace. CLC, so basically make it clean slate so I don't have any variables saved. It's just whatever's built into Matlab at that point. CLC is clear the command window, so erase everything that's there. So I have a clean slate on that, and then close all. So if I had any figures open, close all of them. And then I'm going to make two variables. So I have two knowns. I have temps and times hours. So I'm going to just put those into matrices so that I have that data stored so that I can reference it, right? Then what did I do in working through it by hand? I looked at the first, and then I checked if it was greater than 102. So I went through every point in temps and found the corresponding time hours. So I'll need to know where I am located in temps. So I want to work through, again, everything in temps. So I want to see, first of all, how big is temps? So the size of temps, size temps is size of temps. And that'll give me how many rows, how many columns. If it had depth in the third, fourth dimension, it'd give me how big those are. And then I'm going to make a list. So first I want it to start out as a blank list. And in Matlab, I'll just use a matrix to store the list data, right? So in this case, I'll make an empty matrix. So just open bracket, close bracket. All right, then I want to go through everything in temps, right? So I want to know, okay, for day, so I'm going to loop because I want to do a repeated operation. I'm just going back like on here. If I'm circling back and doing the same thing, I want to do a loop. So I'll try a loop. So for day, and day is the number of rows, right? The first row is day 1, the second row is day 2 for the data I'm looking at. So I say for day, which is a variable I'm making for to populate with the values that says is equal to. So it'll be the first in this and then the second in this, so on. So I'll say for day equals 1 colon size temps of 1. And what will this do? It will give day first, the first value in this, second, the second value in this, third, the third value in this. But what is this? This is 1 colon size temps of 1. So it's 1 colon, in this case, it'll give you the number of rows of temps, which in this case is 2. So it'd be 1 colon 2, which would just be the matrix 1, 2. Like this. 1 and 2. Okay. There you go. So now we've gone through the days. Let's go through each of the times in the days. So for time equals 1 colon size temps of 2, which is the number of columns. So I want to go from 1, 2, 3, and 4, which 1 colon, because I didn't include like a 0.5 or something as the increment size, right? So in a matrix, I can, if I wanted to do 1, 2, 3, I would do the start number, 1, the increment, in this case is 1, and the end, which is 3. But MATLAB automatically will assume 1, so if you just do 1 colon 3, it will work. So I'm just working through. I want it to do 1 to 4, so 1 colon, and I'll just have it handle the computation for me. So if temps were to change, it would still work by using size temps of 2, number of columns, 1 colon 4, 1, 2, 3, 4. All right, so then for that day, it'll start at the first day and then look at the first time in that day. So it'll start at 101, just like we did working through it by hand. And then it'll say if temps at the row is the day and the column is the time. So it'll look, first it'll start at day 1, time 1. Is that greater than 102? That would be 101. If it were greater than 102, then times greater than 102 of length of times greater than 102 plus 1. So length is how long it is. If it's just a one-dimensional, because we'll want a list, so it'll just have like 1, 2, 3, 4, 5. It wouldn't have rows and columns. So times greater than 102 at the size of it plus 1. So at the next open spots, because the length of it right now is 0. So we want to put it at the first spot, equals, and then we'll look at the times, hours, and then look at the same position, the day and time that we were looking at with temps. And that will go into the list in the case that it's greater than 102. In this case, it is not greater than 102. So this is not met. It will not perform any of these operations and it will end immediately. We'll get to this end and then we'll circle back. Okay, have we gone through everything in size 1 colon size temps? Nope, we need to go do time 2. Time 2 is 102, which again is not greater than 102. And this is the end of the for loop. So circle back for 101, we'll do the same thing and circle back. And then 104 finally. But again in here, this is time equals 3. Day would still equal 1, of course. So temps at day 1 time 3 is row 1, column 3. Or excuse me, it won't be till row 1, column 4. So as soon as we got to the fourth one, right here, 104, temps of day and time will give you 104 is greater than 102. That's true. So then times greater than 102, this would still be 0 because there's nothing in times greater than 102 yet. So you add 1 to that. That's the first position in times greater than 102 equals the times hours at that day and time, which in this case is day 1, row 1, time 4, column 4. So we'll go here, look at it, and that will be added to the list times greater than 102. And we'll end it, and now we are done with going through all the times in that day, end it, but now we end this, which means we circle back because it's a loop, and go to the second value of for day, and go and do the exact same thing. And loop through the times again. That will give you 103 and 106 are greater than it, so it'll give you 107.1.3 and 107.7.5. And it will add all of these into the next position in times greater than 102. All right, so if we look at the times hours in times greater than 102, we can just pop it out into the command window with this. Display nothing, just have some spaces, and then temps greater than 102. So we can see, if we look at the output of this, what is this making? Let's look, including the times hours stuff, because all the rest are suppressed. The output times hours is this, 1e plus 3, so 1,000 times each of these. It's just how Matlab is formatting the numbers to display to you here in the command window. So times hours, these are the hours times greater than 102, 1051.1, which is that times 1,000, 107.1.3, and 107.7.5, which is exactly what we expect it to output. So that's the one here, here, and here, right? So if we look at temps, we can say 101, 102, 101, 104, and so on. Then with the temps greater than 102, we can just look through and it will return a matrix the same size of temps, but with a true or false if this condition is met in every case. So this 101 is greater than 102, right? That is 0 because it's false. 102 is greater than 102. Again, 0 because it's false. 101 is greater than 102. Again, 0 because it's false. Until you get to 104, and this is true, right? So in this example, it's pretty easy to visualize it ourselves, but we could use, let's say we had a huge temps and times hours matrix. We could use something like this to do a real quick check. Okay, it looks like it's working because we can have it find all the positions that are too great of temps and then look at the times hours at those points and then have it make sure it aligns with what we expect here. So that's second example of how you could approach problem solving in Matlab.